Hello students. Welcome to our Senior Secondary 2 Physics lesson. Today, we will be exploring more about simple harmonic motion, identifying the examples, formulas, and relationships in simple harmonic motion. But before we proceed, let's quickly recap on what we learned from the previous lesson. In our last lesson, we understood the concept of simple harmonic motion. We learnt about speed and acceleration of simple harmonic motion. We also went further to explore period, frequency, and amplitude of simple harmonic motion. And it was very interesting. Before we proceed to today's lesson, let's take a quick look at our lesson objectives. By the end of today's lesson, you will be able to know the examples of simple harmonic motions, identify the formulas for simple harmonic motion, also understand the relationship between period and frequency in simple harmonic motion. Are you ready? Sit tight, let's dive in. Let's explore some examples of simple harmonic motions to see how motions work. 1. Pendulum motion. A simple pendulum swings back and forth around its equilibrium position. The restoring force is gravity, acting to pull the pendulum back to the center. Here, speed is maximum at the center, while acceleration is maximum at the extremes. Applications of pendulum motion. Timekeeping. Example: the pendulum clock. Other examples are swings and amusement rides. Pendulum-like swings make rides fun, while illustrating the principles of periodic motion. 2. Spring mass system. When a mass is connected to a spring and moved from its resting position, it oscillates back and forth around its equilibrium point. At the equilibrium position, the speed is maximum, and the restoring force is zero. Here the spring stretches and compresses alternately. Applications of a spring mass system. A spring mass system has various real-life applications, including gym equipment, springs and dampers in vehicles, and so much more. 3. Motion of a swing. At the equilibrium position, the speed is maximum and the restoring force is zero. The motion is repetitive. Applications of motions of a swing. Seismometers detect ground motion during earthquakes through pendulum oscillations. Engineering structures. Understanding pendulum motion helps design structures like bridges to resist oscillations. And so much more. You can go further to research more about the application of these examples of simple harmonic motions in real-life scenarios and see how interesting it is. Now let's see the relationships between period and frequency. Period is the time it takes for the object to complete one full cycle of motion, back and forth. And frequency is the number of complete cycles the object makes in 1 second. Period is measured in seconds. Frequency is measured in hertz, where 1 hertz equals 1 cycle per second. The two are inversely related. F equals 1 over T, and T equals 1 over F, where F is frequency, and T is the period. For example, if a pendulum swings from one side to the other and back again in 2 seconds, its period is 2 seconds. So, if the period is 2 seconds, using the formula, the frequency is 1 over 2, which equals 0.5 Hz. Period and frequency describe aspects of repetitive motion, like vibrations or oscillation. Next, let's talk about the formulas for simple harmonic motion. Let's recap a little. In our previous slide we looked at period, T, and frequency, F, showing their formula, that is inversely related, which is T equals 1 over F, and F equals 1 over T. Let's clearly note that T is the time for one oscillation. F is the number of oscillations per second. Example: a pendulum completes 30 oscillations in 15 seconds. We need to calculate period, T, the time for one oscillation. Frequency, F, the number of oscillations per second. Solution. Stating the formula. T equals total time for one oscillation over number of oscillations per second. Given the values, t equals 15 seconds over 30 oscillations, which equals 0.5 seconds. Now, calculate the frequency. F equals 1 over t. F equals 1 divided by 0.5 seconds, which gives 2 Hz. It's not so difficult. Now let's find out the formula for solving restoring force. Restoring force. Hooke's law. Here is the key formula to find the restoring force, Hooke's law, in simple harmonic motion, along with an example for better understanding. Hooke's law states that the force F needed to extend or compress a spring is directly proportional to the displacement x of the spring from its equilibrium position, provided the elastic limit of the spring is not exceeded. Formula: F equals minus kx. Explanation: F is the restoring force acting on the object. K is spring constant in newtons per meter. X is the displacement from equilibrium in meters, m. For example, if a spring has a constant K equals 10 newtons per meters and is stretched by 0.2 meters, what is the force? Solution: substitute the values into the formula. F equals minus kx. K equals minus 10 newtons per meter, and x equals 0.2 meters. Now, F equals 10 newtons per meter times 0.2 meters. Therefore, F equals minus 2n. The negative sign indicates the force is directed toward equilibrium. Hooke's law shows that the force exerted by the spring increases proportionally with displacement. Well done, you're doing great. Now it's your turn. Here are 2 quick practice problems. Give them a shot. Remember to pause the screen and solve the problem. Excellent work. You've done a fantastic job following along with today's lesson. Let's take a moment to review what we've covered. Period and frequency are inversely related with their formulas. All these motions have real-life applications. We calculate restoring force using the Hooke's law. In our next lesson we will be learning about equilibrium of forces. Well done. You've come to the end of this lesson. Keep practicing what you've learned. I will see you in the next lesson.